Hello students, good morning. So in this lecture we will be starting with module 2, and module 2 is your spectroscopy techniques, okay, and its applications. So today we will discuss, means we will just see a brief introduction to spectroscopy. Okay, this will be new because you won't have means this spectroscopy, this subject is not included in your class 12 and 11. Okay, you have not got that things, so it will be totally new for you guys. So let's start with it. Just the basic things we'll discuss it today. Okay. So you see, we have electromagnetic radiations. Okay, we have electromagnetic radiations. Okay, now what are electromagnetic radiations? You see, say you have a electric field, okay, and you have vibrations in that field. We have electric field and we have electric field vibrations. Okay, so say the electric field is moving like this, okay, this way, and we have, say, magnetic field. So magnetic field also same like this. Say let us give it with this one, like this. Okay, means the magnetic field, it is moving in this axis. Okay, mean say this is x axis, this is y axis, and this is z axis. Okay, and say, yeah, for this one also x, y, say z. Okay, now you can see that this this is, say, magnetic field vibrations, and this is electric field vibrations. Okay, now electric field, it is moving in xy plane. Okay, it is moving in the xy plane, means in this plane. This wave is moving in xy plane, whereas the magnetic field, it is moving in xz plane. Okay, now what we'll do, you just see, say we have this as the line, this is we had electric field, it is like this, like this. Okay, and we had our magnetic field, which is in the horizontal plane. Let me draw it nicely. Okay, it is in the horizontal plane. Okay, so just like this. Like this. So you had the z axis this way. So this is x, this is y, and this is z axis. Okay, now initially what we have done, we have I have drawn both these graphs separately. This is in the horizontal plane, this is in the vertical plane. Okay, means the vibrations are going in this one. Okay, and one more thing to you all know, that this is say this is a complete wave, say this one, this is a complete wave. This part is called a crest and this part is called a trough. Okay, and this is the amplitude, this position, the highest peak is called the amplitude of the wave. Okay, this is a complete wave. Okay, and this position, this much distance, okay, one crest and one trough, it is called your wavelength. Okay, so what happens, you see, in this one, when the electric field vibrations, okay, this is electric field vibration, okay, and this is magnetic field vibrations. When the electric field vibrations and magnetic field vibrations, they propagate in the same direction. You see, they are in different planes. Okay, they are vibrating. This one, the red one, that is the electric field, is vibrating in this direction. Okay, it is vibrating in this direction, means xy direction. Along the y axis it is vibrating. Okay, whereas you see this one, the purple one, the blue one, the magnetic field, it is vibrating in this direction. Okay, means in the horizontal plane, z plane, it is vibrating. Okay, so both are vibrating into perpendicular planes. Okay, but they are propagating in the same direction. Okay, they are, it is like this, one is vibrating in this way and going in this direction, another one is vibrating in this direction, like this, horizontal plane, but going in the same direction. Okay, so both are vibrating in two different planes but propagating in the same direction. Okay, then this type of wave, this whole type of wave, mixture of electric and magnetic field vibration, is called a electromagnetic wave. This type of wave is called electromagnetic wave or radiation. Okay, electromagnetic wave or radiation. Okay, now what happens, you see, this electromagnetic waves, okay, this electromagnetic waves will have some wavelength represented by lambda. Okay, they will also have some frequency, nu is represented by mu. Okay, they will have some frequency. Okay, wavelength means this one I have already discussed, means the means distance of a complete wave. Okay, means say if the wave has started from here, so one crest and one trough, this much. Okay, so this much length is called the wavelength. We have frequency. So frequency means number of waves through a given point per second, number of waves per second. Okay, number of waves per second means, say if we consider this point, so we have this point, so the wave is going this way. Okay, now if you consider this point, okay, through this point how many waves are propagating in 1 second, that much will be the frequency. Okay, now this wave have some frequencies. I have what I was saying, this electromagnetic waves. Okay, this electromagnetic waves will have some wavelength, they will have some frequency. Okay, now when we arrange, okay, see we arrange this all these wavelengths, means in this electromagnetic radiations, all the different wavelengths that we'll be getting, will arrange all this in terms of, say, increasing frequency. Increasing, all the waves are arranged in increasing order of frequency. Okay, and decreasing order of wavelength. Decreasing order of wavelength. Okay, now when these are arranged in increasing order of frequency and decreasing order of wavelength, we will get a spectrum. Okay, so we will get some regions like this. Okay, we will get some regions. Okay, so that is called a spectrum. Okay, that is called a spectrum. Now in the spectrum, what we have, you see, first we will get this one, NMR, then we will get ESR. Okay, then we will get microwave, then we will get IR, means infrared, then we will get ultraviolet and visible. Okay, then we will be getting X-ray, then gamma ray. Okay, like that. Okay, means all these are, you see, arranged in increasing order of frequency. Okay, increasing order of frequency. Now this NMR and ESR, they belong to radio frequency, means radio waves. Okay, these are means these are these waves, radio waves, they have the least frequency. Okay, least frequency, that's why what happens, since they have the least frequency, whereas this gamma wave has the highest frequency. So the order is like this. Say you have, for this one, just let me give you the values. So this one will be 10 to the power 6, 10 to the power 8, then 10 to the power 10, 12, 14, 16, up to 10 to the power 18 it will go. Okay, this is the values of frequency. Okay, for wavelength, say it will be like this. So it will be 10 to the power 2, yeah, then this will be 10, this will be 10 to the 3, okay, then 2, then will be 10, then minus 2, minus 4, minus 6 will be minus 8, like that. Okay, this is wavelength, this is decreasing. Now you see, when you have this one for radio waves, the frequency is very less. Okay, the frequency is less, that's why it is less harmful. That's why you see now this radio is you see now this one. Just give me a minute. Yeah, we all have this one, no? FM radios and all. So you all hear this one, no? Where you hear songs and all, FM radio. So this FM radio, no, this or the radios and all, they use this frequency. Okay, they use this frequency for their this one programs and all to telecast. Okay, whereas microwave, it is also having less frequency, so it is also less harmful, because you can cook food in microwave. So if microwaves are harmful, so if you cook food, then it will be harmful for you. Okay, so you see these waves which has less frequency, those are less harmful, whereas those rays or wavelengths which has more frequency, say gamma ray, x-ray, those are more harmful. Okay, you see x-ray, what happens if you pass x-ray, it will penetrate your body through your bones. Okay, and gamma rays though are used to break a nucleus. Okay, say for in nuclear fusion we use gamma rays. Okay, these are very very harmful. Okay, because these can penetrate through anything. Okay, and we had IR, infrared, whichever you use in your television remotes and all those things. Then we have UV visible and all. Okay, UV visible is UV rays are a little bit harmful because they belong to the higher frequency region. Okay, but infrared is also means you can tolerate. Okay, because they have less penetrating power, because they are less harmful. Okay, so in this way, what happens when we arrange the electromagnetic radiations in increasing order of increasing order of frequency and decreasing order of wavelength, we get a this one spectrum. Okay, and this spectrum is called your electromagnetic spectrum. Electromagnetic spectrum. Okay, this spectrum is called your electromagnetic spectrum. Okay, now you see, now yeah, this much. Okay, now you see what is spectroscopy. Okay, now spectroscopy is nothing. Say spectroscopy, it is nothing but a branch of science. Okay, and you have different this one rays now. So what we do, we use all these rays in different uses. Okay, so in chemistry, what is the use? Say we have prepared a synthesize, say we have a reaction X plus Y, and it will give you Z. Okay, this is the reaction that we have done. Now this Z, the new molecule that you have formed now, we don't know the structure and properties of this molecule. Okay, we don't know anything about it. Okay, so what happens when we use the spectroscopic techniques? There are many spectroscopic techniques, we will discuss it. So using those spectroscopic techniques, what we can do, we can identify the structure of this molecule. Okay, we can identify the structure, its properties. Okay, and many things, means all the informations regarding an new molecule or atom. Okay, anything can be identified or determined using spectroscopic techniques. Okay, and spectroscopy is also used in many other uses also, means in medical sciences also spectroscopy use say when in order to obtain a x-ray of a body, what we do, we pass x-ray through which it scans the, and say you had a fracture in bone, so that is identified by spectroscopic techniques, means x-ray they are using. Okay, x-ray photography. So there are many things, many uses of this branch, and it's very very important. Okay, so now you see what you have listened. Yeah, one more thing, this one spectra na? See how, what is this is the branch of that I have discussed, the spectroscopy. Now what is a spectra? You see, we have different energy levels in an atom, means how spectroscopy works. Okay, how we can identify, determine the structure or different properties of a molecule or atom. So we have a different this one energy levels. Okay, these are the different energy levels. Okay, so this is E0 ground state, this is E1, this is E2, this is E3, dot dot dot, like that. Okay, now what happens, say we have a electron, in this position. Okay, now if we give, say if we provide some external amount of energy, okay, say delta E. Okay, just let it be E. Okay, just let it be E, yeah, E, say AX. Okay, this is the amount of energy, okay, that we are giving. As soon as this this electron, it gets the energy, what will it do? It will jump. Okay, it will jump to some higher energy levels, like this. Okay, now when this electron, it will absorb this energy. Okay, it will jump to this E2, from E0 to E2 level. Okay, now this energy that we are doing, okay, means that we are providing to this electron, this energy will have some, this EX will have some wavelength, and since it will jump from this one to this one, it will also have some frequency. Okay, now we will check where this wavelength or frequency belong, means which part of the spectrum. Say if it is in 10 to the power say 10 to the power minus 4. Okay, if it is in 10 to the power minus 4, if the wavelength it has a value of 10 to the minus 4, then we will know that it falls in the UV visible region. Okay, say for frequency also you can check. So frequency for UV visible will be 10 to the power 14. Okay, so it will be 10 to the power 14, like this. So this frequency and wavelength that we can calculate, there are several instruments. Okay, so UV spectrophotometer we have, infrared spectrophotometer we have, then NMR and IR, we all can take all these things, okay, using different instruments. Okay, so instruments things we will discuss afterwards. Okay, so what happens, this energy will correspond to a wavelength and frequency. Okay, so from that one we can understand what is the frequency, means what is the frequency of light used. Okay, means what is the ray, then we can use that ray to study the this one structure. Okay, now this will give rise to a spectra. Say when we put this thing in the spectrophotometer, we'll get a spectra like this, anything. Okay, it will get a spectra like this. Okay, so from this spectra we can study the spectra and we can find the different properties from that one. Okay, so this spectra, it is resulting from this one absorption of energy, because we are giving energy, it is taking the energy and it's jumping to the high energy level. So this spectra will be called as absorption spectra. Okay, this is one type of spectroscopy. Okay, this is one type of spectroscopy, it's called absorption spectra. Okay, now you see just the basic law of nature. Now if everyone in this nature tries to stay in this low energy level, okay, most stable state, everyone tries to be in the most stable state. Okay, so what happens, this electron, when it takes the energy, it will move to this E2 level. Okay, but it will be unstable, this one will be unstable because it is having higher energy. Okay, this one will be unstable because it is having a higher energy. So it will always try to give its energy. Okay, it will always try to give its energy and come to a back to this ground state. Okay, means low energy level. So what it will do, it will give its energy, say EY it is giving out. Okay, it will give its energy EY and it will come back. Yeah, it will give the energy and it will come back in this level again in the ground state. Okay, so for this energy also, means whatever energy it will give EY, that will also correspond to some this one, that will also correspond to some wavelength or some frequency. Okay, so for that also we'll get some spectra, like this. Okay, so that spectra will be called as emission spectra. okay, that will be called emission spectra. Okay, so we have two types of spectra. First one is absorption spectra, second one is emission spectra. Okay, absorption spectra results from absorption of energy, okay, that the electron takes, and emission spectra will result from emission of energy. Okay, this is the basic principle of spectroscopy, where we get the spectroscopy. Okay, so I guess it will be clear now. See what we'll do, we will discuss these things. Yeah, one more thing I have left out. You see, this energy, how it is related to wavelength and frequency. Okay, this is given by the Planck's quantum theory. Okay, Planck's quantum theory. You know that Planck's quantum theory you have studied in class 12. It states that energy is not continuous, it is in discrete levels. Okay, means energy, say we have this one, we have the sun. Okay, we have the sun. Okay, now say this energy from the sun is coming like this. Okay, this is, see, this is you. Okay, energy from the sun is coming to the earth. Okay, now see what happens. This energy, it is not flowing in continuous form. Okay, previously in classical mechanics or classical theory, what we got is that energy flows like this, like waves. Okay, continuous motion. Okay, but actually it is not like this. Actually, then energy is like this. Okay, means it will be like this. Just give me a minute. I'll draw up my screen. It will be like this, like packets. Okay, means like small energy packets, and each packet is called a quanta. Okay, each energy packet is called a quanta. Means just like raindrops, you can see raindrop, it is not continuous now. The rain falls from the sky in terms of small drops. Okay, so the light from the sun also comes in small energy packets called a quanta. Okay, and each quanta has an energy of En is equals to nh nu. This is the relation between this one, energy and frequency, where h is your Planck's constant, and value of h is, and the value of h is 6.626 into 10 to the minus 34 joules second. Okay, minus 34 plus 34, plus minus 34 na, yeah, please check it either it's minus or plus. Okay, so it will be 6.626 into 10 to the minus 34 joules second. Okay, and this one, this unit is very important. Okay, always whatever calculations you do either in physics or chemistry, unit is very important. You just keep this one in mind. Okay, so now you see this is the basic relation between this energy and frequency. Okay, now frequency is also related to wavelength, as nu is equal to c by lambda. Okay, nu is equal to c by lambda. So this c is nothing but speed of light, which is 8 into 10 to the power minus 3 into 10 to the power 8 meter per second. Okay, this is the speed of light. Okay, lambda is wavelength. Okay, and lambda is expressed in centimeter, okay, or meter. Frequency, its unit is hertz or second inverse. Okay, that's the unit frequency. Then we also had one thing, relation between lambda and nu bar. Okay, nu bar is nothing but 1 by lambda. Okay, nu bar is 1 by lambda. Nu bar, what is nu bar? Nu bar is the wave number, means number of waves passing through a point in a given time. Okay, that is nu bar, it's called the wave number. Okay, so from these two equations we can derive this one, that nu will be equal to c nu bar. This is the relation between frequency and wave number. Okay, so these are the basic relations that you can derive from this one. One is this one, E is equals to n h nu. N is just number. Okay, it is number of moles. Okay, how many or number of waves. So each energy, say we have 10 packets, so n will be equal to 10, and this one h nu will be the energy, okay, associated with each packet. Okay, So this one we have equal to nh nu. We had this one for frequency and lambda. This is for wave number and wavelength, and this is for frequency and wave number. Okay, so these are the basic formulas that we'll be using for this one in this spectroscopy. Okay, now what we'll do, you see, yeah, so this, I think this will be it, the basics for spectroscopy. We'll also discuss some selection rules. Okay, so I think it will be it for this class, so thank you. So again, let's resume the lecture. Okay, so in this part, you see, this is the principle of spectroscopy we have already discussed. Okay, then we had this one, two different types of spectroscopy. We had atomic spectra and molecular spectra. Okay, just now I have discussed now that is how spectra occurs, say absorption or emission spectra. Okay, now if the electronic transition takes place in atom, then it will be called the atomic spectra, and if it takes place in a molecule, then it will be called the molecular spectra. Okay, now you see, this is the table. Okay, this is the different types of molecular spectra. We'll get to study UV visible or electron spectra. We'll study microwave or rotational spectra. Then we'll study vibration or IR spectra, infrared. Then we'll be studying Raman. Yeah, Raman is not there in his syllabus. Okay, we will not study. NMR is there. We will be studying NMR, and electron resonance spectroscopy, ESR. It is also not present. Okay, so we will not study this one. Okay, so you see, yeah, this one. Now see what happens for the spectroscopy. Now we have some selection rules. Okay, that governs the width and intensity of the spectral lines. Okay, now see, intensity means, say a spectra is like this and a spectra is like this. Okay, this spectra is more appropriate because it is, means the peak is sharp. Okay, so it will give us most means more appropriate values or information about the molecule. Okay, but for this one, the peak is broad. Okay, so this type of spectra will give us less information, so these are less appropriate. Okay, so what are the reasons that causes this broadening of the spectra? Okay, the first is collision broadening. Say in a molecule, say if you have a sample liquid or gas, all the molecules will be in continuous random motion. Okay, so when they will be in continuous random motion, they will collide with each other. Okay, and that will cause to the, means the spectra will become wide. Okay, means it will cause broadening in the spectra. Okay, because the molecules will get deformed if they collide with each other. Okay, then we have for Doppler's effect. The Doppler's effect is also a reason for broadening of the spectra. See, these things are not that important, so you just read it once. Okay, and if it comes in exam, you just have to write this one. Okay, because if you go into detailed explanation of these things, it will be, say it will be taking say 3 or 4 classes. Okay, so then one more thing is there, lifetime broadening. Okay, that is governed by the Heisenberg's uncertainty principle. Heisenberg's uncertainty principle, you all know that we cannot calculate any two physically observable quantities or properties simultaneously. Okay, and precisely, means just like that one, say for an electron we cannot identify the position and momentum or energy and time like that. Simultaneously you cannot calculate both precisely. Okay, so these are the three effects that this one, yeah, this collision broadening, Doppler broadening, and lifetime broadening, these are the three reasons for broadening of the spectra. Okay, now intensity of spectral lines, how we get more intense spectra. Okay, for this one we have transition probability and population of the state. Okay, now transition probability means, say we have this one energy level, and we have two energy levels like this. Say these two energy levels have same energy, so this one is electron, this one is electron. Okay, now this electron can also jump to this one, this electron can also jump to the higher state. Okay, both can jump. Okay, now you see, whichever electron means whichever energy state has more number of electrons, say this one is E1, this one is E2, and this one is E3. Okay, now say E2 has 3 electrons, E1 has 1 electron. Okay, then the probability for E2, this 3 electrons from E2 to jump to E3 will be higher. Okay, because there are more electron density. Okay, So since this probability is higher, that's why this peak will be intense. Okay, so from that one you can identify the intensity of the spectral lines, and this law is given by the Boltzmann distribution law. Okay, and the expression is this one, where n is say number of electrons in the excited state and naught is number of electrons in the ground state. Okay, ground state means this one, the low energy states are called ground state, high energy states are called excited state. Okay, k is Boltzmann's constant. Okay, it has a value of 1.38 in 10 to the power minus 23, I guess. Okay, and T is the temperature, and delta E is the change in energy, means energy difference between these two levels, the ground state and the energy this one excited state. Okay, so these are the selection rules that you have to remember. There we have three rules for broadening of the spectra, and we have this one, three rules for broadening of the spectra and two rules for intensity of the spectrum. Okay, so this is important for you, so you just read it once. Okay, from next class onwards we will discuss these things in details. Okay, so thank you.